I think we can start with today's seminar presentation. Last few weeks, we had a guest from industry, small businesses. Today's guest is from one of our labs, Data Mining Lab. TJ is our PhD student. He's working currently in Data Mining Lab, and he is finishing his dissertation. He completed undergraduate study in India, GITAM University, if I spelled correctly, in 2012, and then Master of Computer Science at University of Louisville in our department. His research interests: streaming data, constructive detection, adversarial machine learning, and bio-inspired algorithm scalability computing. TJ for several years here. He is working on these adversarial machine learning, in machine learning problems for several years, and some of these topics is part of his dissertation, not everything, but some of the idea in his dissertation will be presented here. So I'm welcoming TJ, and the title of the presentation for today is Adversarial Machine Learning When Good Learning Leads to Bad Security.
Thank you. Thank you. Hello, everybody. Yeah, that's the title of my presentation. I'm just going to jump right into it. And before I go into the topic and what adversarial machine learning means, what's good learning, what's bad security, I just want to start off with a small question. And this is kind of the argument and the discussion. Probably I'll just use it in my dissertation's introduction as well. So I'm sure everyone has at this point learned about classification, right, over here. You have two classes of data and you're trying to find a separating hyperplane or some kind of a function that separates both of these classes. So my question is, without any domain information at this point, what's a good function to separate these classes? You have your linear classifier, which is your standard SVM or any kind of linear classifier, and you have some kind of a nonlinear function that fits more closely to the data. So which one at this point would you think is a good model, and why?
The linear classifier.
Why?
Much simpler and not overfitted to the data as in the other case, which is a nonlinear.
Okay. That's a good answer. Yeah, this is what I was looking for, so I could just take it. But does anyone else have any other point to add to that? Or cool. Yeah, that's what machine learning teaches us. So try to take the simplest model that you can, follow the Occam's razor, and as long as it does not overfit, you'll get a good training and a testing accuracy, right? And now we'll forget about this image, and I'll try to come back to it towards the end of our presentation. Just a brief background. So machine learning is in all walks of life. Even cybersecurity has to accept machine learning because the scale and the sophistication of attacks now is just too big that we cannot rely on simple signature-based or rule-based approaches to just deal with them. We have to resort to some kind of interpolation from data, something that we have seen, and try to learn from that. Those are just some of the examples of recent attacks that we have seen in the last 2 years, and just how many million records they had compromised. So just to give you a sense of what scale we're talking about. As far as applying machine learning and cybersecurity is concerned, there are different machine learning techniques that have been used. There is the anomaly detection, which is the most commonly used technique. The other classes are classification and clustering. Our talk is mostly going to be concerned with the classification aspect. And there are many applications in cybersecurity which use classification. There is your spam detection, there is your capture systems, there is phishing, and click fraud detection. So there are many aspects that deal with it, but we'll try to take a more domain-independent approach to this problem. Few motivating results which are already seen in literature. Most of these are taken from references, which are in the notes over there. And the general trend tends to be that you can use machine learning and get amazing amount of predictive performance, and that it's a good fit. Mostly people try out different models. They try out neural networks, deep learning, SVM, and they go out and they say they have 95% accuracy, so machine learning is the answer to everything. looking with this, owing to this success, there are like now black box prediction systems that are available, like Amazon's machine learning system and Google Cloud Platform's machine learning system. So these are just API interfaces. You can take a database, you can take a data set, you can have a class label column, and the rest of them could be features, and you could just upload it to one of these platforms. You can call a function called predict. It'll train a model for itself, and you can just call a function like predict this sample. You don't have to be worried about parameter tuning. You don't have to be worried about selecting the model. You don't even have to be worried about what kind of model tuning you need to do. So this serve to be like good black box environments where people who have no background information about machine learning can go ahead and use like a spam classifier for their website or their blog. This is very timely. Most of this is still in the beta phase, and this is already being used. So this research, I think, is very timely, especially it comes at a time where people are accepting that machine learning is an out-of-the-box solution, and you don't really need to know the internals of machine learning to be able to use it. A little background into how classification works. You have two classes. You use a training algorithm, which could be anything of your choice, and you try to make a separating hyperplane so that generalization and predictive performance is maintained. In cybersecurity, one of these classes is the good class, and the other class is a bad class, talking about a binary case over here. And as long as you have a good training model, which does not overfit to your data, the assumption is, while you have unseen testing data, your prediction will continue to be good, or almost as good as what you were expecting. But there's an important assumption that is often missed out over here, that the data has to be stationary. Only if the training and the testing data follow similar distributions is this assumption valid, that your performance will continue to exist. But what we argue is, why should an attacker keep generating the same data if he's getting blocked out in the first place? So why would he keep generating in that space if he's getting blocked out? Shouldn't he like modify his approach? And what will happen if he actually does that? And that's kind of like the foundation for adversarial machine learning. A simple example over here, let's say you have this classifier. An attacker can make like a simple probing sample, send it to the system, see that it got rejected. Try another sample, got rejected. Same thing. Until finally he gains access to the system. At that point, he can take this sample as a seed and then start exploring area near that. And this is the idea that we try to explore in this very initial idea of experimentation. We tried this on three popular cybersecurity data sets: the capture data set, the intrusion detection data set, and the spam data set. And all of them, based on our initial 10-fold cross-validation, we saw that it had good accuracy. And we were convinced that it was a good model. But using this model of an attack, a very simple model of an attack, we found that it took us less than 30 probes to get the first green sample into the model. And then after that, we were able to generate attacks which were at least 75% accurate. So this shows that our idea of accuracy, our idea of security from machine learning is kind of flawed, and we need to like look at it from a different angle. Raising the important question, if accuracy is security, and is machine learning actually safe? Yeah.
I have a question. The previous question, was the last column to the right indicates that you started just getting random samples just to challenge the previous accuracies achieved?
So after I get the first green sample that goes into the system, I generate a set of, let's say, 1,000 samples, and I check
around this green one.
Around this green one.
And you find that the system didn't detect all of them.
Yeah.
Most of them.
For 92% of the time, even though these were attack samples, the system said it was okay. They are legitimate.
Was it detected? Or was it
was detected as a good sample, even though it was actually generated as an attacker, as a bad sample.
Yeah, so this is a failure to the system.
This is a failure to the system. Yeah. That is kind of the background. And this is the idea of adversarial machine learning. Like, how can machine learning be evaded? What are the actual problems with machine learning? When an attacker is actually a little bit smart, he knows about machine learning himself, might be a data scientist who's trying to break a system. So based on this, we make the seed, explore, exploit framework, which is our framework where we act like the bad guys. We try to be the attacker and try to see if we can attack black box machine learning systems. How the attacks actually work is like this. Consider this simple example of a captcha system. This, if you know, is the Google's reCAPTCHA system. You take your mouse and just click on that checkbox over there, and just by your motion and some internal features, it can actually predict whether you are a human or a bot. You don't have to type out those like really confusing messages and like boxes to make that work. Internally, it's not going to be as simple as that, but that's just for illustration. Let's say it is taking two features, the speed of your mouse and the click time. This is, as far as I'm concerned as a data scientist, I develop this and deploy it over there, and I forget about it, considering I have 100% accuracy. As an attacker trying to gain access to the system, I don't see the internal model, but I do have access to the system as a client user. And what I can do is, I can submit some samples, which in this case is nothing but me making bots and changing different parameters to the system. And this is pretty standard. The click time graph is available online for human response time. And based on that, I can make different probes. And I can gain access. At this point, I can understand that any click time greater than 280 samples, 280 milliseconds, will get accepted by the system. Internally, this is how the probes would look like. And even though I did not successfully reverse engineer the entire landscape or the prediction, I can still, using my limited knowledge, actually gain access into the system. Another example of this that I was trying yesterday might be interesting is, let's say, sorry about that. So I found this online classifier. Oh, you can see it. Maybe I'll show it to you, and then that might be better. Okay, so I found this online classifier which trains a model and just like demonstrates it as an online toolbox. Nothing fancy about this. Internally, I don't know what it is using, but I just know if I enter a text over there, it will tell me whether the sentiment expressed is positive or negative. Now, something like this, let's say, is an interface to a website that I'm selling, and people can come in and comment on my products that I'm selling, and the comments could be either positive or negative. Since I'm a bad seller and I don't want bad comments to come on my website, I make a classifier to weed out all the bad comments. So this classifier will let only good comments be posted on my website. Okay, so if I post something like,
could you please turn off those lights over?
Which one?
Turn the lights.
I think on the back, maybe.
Because of recording.
Oh, okay. Go ahead.
Okay, so I just posted a comment that said, I hate this product, I don't want to buy it again, and I wouldn't recommend it to anyone. Okay. I classify it based on this model, and of course it is 99% negative. So it will get stopped by the classifier. But I'm really pissed at this company, and I want to like post about it. So what I started doing was I started trying different word combinations last night, and turns out emojis have a very big impact on the classification performance. So for this message to get accepted by the system, 8 emojis is the threshold that I found out. So I did that. It's 58% positive now. I can keep adding emojis and it'll be like the most positive message that was ever posted. And look at the message. The message is, I hate this product, I don't want to buy it again, ignore the emojis below, and 8 emojis. Something like that. So this is kind of like a real world example of the adversarial problem that we face. Like, I'm not a machine learning scientist when I'm doing that, but with very simple probing of the system, I can see what goes in and what does not. And So that was a simple example of how an adversarial machine learning, how an adversarial sample will work. But taking that simple intuition and applying machine learning to it from an attacker's perspective, we can see that adversarial machine learning is a problem in itself, and it has to be dealt in a machine learning perspective. Now, anyone who has taken any kind of heuristic optimization or search techniques is very familiar with the seed, exploration, exploitation approach, right? You start off with some samples, try to explore a few possible good directions, and then you exploit directions which work very good. We define attacks in the same idea. So we start off with a good sample, some message which we know will get accepted by the system. We try to modify a few of the words and see up to what extent we can go, and the system still thinks it's good or bad. At the point where we reach a bad sample, we have reached some kind of a boundary, and we can exploit this information to generate samples which we want to get into the system, but which might be advertisement, which might be spam, but something that fools the system. This is the general framework that we are defining, and we say that there can be many different algorithms that can be developed using this framework. Two of the algorithms we propose in the work that we are doing, and the first one of this is the anchor points attack. Again, we are going to go back to the geometric aspect and data mining aspect of it, and it will relate it to the real world later on. So you start off with 2 class samples. In the seed phase, you start with one attack sample, which is your seed. You start, anyone who has done mean shift clustering will know that you start off with a radius of samples and start expanding it to see around the same concept, how much is accepted, how much is rejected. Then once you have these samples which actually went into the system, you exploit that information to generate more samples. And you can do that using convex combinations of these points. This becomes your attack payload, and as you can see in this example, most of it are on the positive side. Even though they are negative samples, they are actually attacks. Now, this was a simple example of an attack strategy. You don't have to have much information about the model, about the data set or anything, but it does the job. Another more complicated technique that we have been exploiting is the reverse engineering attack. You start off with 2 samples this time, one positive, one negative. You do orthonormalization on the midpoint of these samples, generate some more samples along the line, and ultimately reverse engineer your model. This attack is a much more serious case of attack because we actually know what you think is good or bad, and we can totally deceive you in the bigger picture. If I know exactly what you know, you have no defense. So we think that this attack is a much serious case. One thing that we want to highlight is in our attacks, we assume that the model is a linear model. I'm sorry, in the reverse engineer, we reverse engineer it as a linear model, even though the underlying model is nonlinear. And this approximation might be considered a limitation, but as we'll see in the experimentation, it doesn't really matter. Even partial reverse engineering is enough to cause a lot of damage to most of the classifiers out there. So the first thing we did was we took 10 data sets. 7 of them are from the UCI machine learning dataset repository. 3 of them are very common for cybersecurity applications. We trained a classifier for all of them using support vector machines, and we found that this was the initial accuracy. The reverse engineering percentage just is a rough metric of how good the reverse engineering was, and for the most case you see that the reverse engineering is not so good, although these have good accuracy. Now, without adversarial machine learning or any other theory behind it, you would stop at this and say that my accuracy is good, my model is good, security is guaranteed. But based on the attacks that we just described, the anchor points and the reverse engineering attacks, no matter what kind of underlying model the defender used, we were able to attack for the most point with reasonably high amount of accuracy. Except for a few cases that we mentioned, most of the time the attacks were successful. Even if you consider the reverse engineering attacks which had low accuracy, you get pretty good attack rate. That proves the point that even with a linear approximation we can do a lot of damage. Another interesting result that we tried recently was we took the Google Cloud Platform and we uploaded the 3 data sets that we talked about. Now, we don't know what Google trains the model as. We don't know what the internal representation is, what the parameters are. And still, we run the anchor points and the reverse engineering attacks through the APIs that they provide us. And we were able to get amazing results for the attack. We got like more than 95% attack rate for most of them. So even though Google advertises this product as one for spam detection, one of the use cases is for comment spam. You can see it on the spam-based data set. Even though a 93% accuracy is provided, the attack rate was close to 100%. So I'm just going to leave this at saying that accuracy is not an indication of how secure a system can be. We need to start looking at different metrics. We need to start looking at different designs of classifiers. And all of this together will help us provide like a better sense of how machine learning can be used for this particular application domain. And this is kind of like the real world equivalent to whatever we have been discussing. Most of the discussions that we have had so far is about points or samples in space, but how they actually convey to the real world is displayed in this slide. So for one example was given by one of the references that I've been reading was, this could be applied to computer vision problems, like for the self-driving cars. 2 images which look exactly the same to a human eye actually lead the classifier to give totally different results. One of them is inferred as stop. The other one was inferred as accelerate. So you can actually, as a competitor or just as a person who wants to do some damage, can fool the classifier like a deep neural network to behave totally differently. Similarly, a recent paper was brought out which shows that home automation systems and voice-controlled home assistants can be fooled using gibberish text. You can like have background static noise, which human thinks is no big deal, and it can actually trigger your home assistant to do different things. So you could actually play a song on the radio and cause 100 million thermostats in the United States to get shut off automatically. So the range at which this works is very scary. And this is again a simple example of a spam data set. If you know that the word sale is getting blocked out of your spam campaigns, people just change the letter L to the number 1. Looks almost the same, but to a classifier it's totally different thing. So this kind of brings it back to what are the real world implications of adversarial machine learning and why there is a need to like tackle this problem head on. That's kind of like the end of my presentation. I don't know, is it too quick or? Yeah, it was quick. Yeah. But if you have a minute, I want to like go back to the initial problem that we were discussing. When we started out the presentation, we said that that model was better, right? Now, knowing that an attacker is trying to get into the legitimate space of samples, does anyone want to change their answer? Is this model better than this? Or not? Or
this model, I believe, you will have undefined area which is not a +1, +2.
Mm-hmm.
So I'm not sure how the system.
So for this one, you could just say anything that's not within this is bad.
To be more secure.
To be more secure. So I was under the impression that that's good too. And I started my research for the last semester trying to do that, but then came across this problem. Consider that this is your attack space, right? It makes it very hard for an attacker to actually reach that small one class of classifier points where you have your training data set. But ultimately, he will reach it if he wants to reach it. It will take some time and effort, but he'll reach it. And once he reaches your point, you're doomed. You have actually told him where the training data is. Your privacy is gone, your training data is leaked, and you can no longer train any more classifiers on this. So maybe a hybrid solution is required. I'm not sure what the answer to this problem is, but it's definitely not this or this is what I'm thinking. Just to kind of give you a motivation for the things that we are working on. We believe that some of the solutions to this might be like a more cyclic approach, where you get attacked, you detect, you get attacked, you detect, and try to stay one step ahead of the attacker at every point. And that's what we're working on, just so you know. Well, thank you. That's about it.
Thank you. Okay. That was more information that machine learning is not totally protected. It was not about solutions.
Yeah.
It is not about how to make machine learning safe. Any question, comments about that?
Yes.
You're welcome.
I have a question about the reverse engineering approach. In the hyperplane, which is highly nonlinear, will this approach also work, or this is almost for the linear classifiers, and in 2 or 3 dimensions is acceptable? In other words, how will you find the midpoint that you start getting the borderline or the threshold in a highly nonlinear hyperplane?
Okay, so in this table, what we showed was all the same data sets. We actually trained with different models. So something like RBF kernel or random forest is going to be highly nonlinear. And as an attacker, I don't know what you trained on. I just assume that some part of it is going to be good, some part of it is going to be bad in the data space. And I'm just going to try to approximate that part using a linear approach. So in this case, even though the Defender model is nonlinear, my linear approximation to it was able to give good accuracy. And most of these data sets were high dimensional. Not super high dimensional, but around 100 dimensions or something.
Complex hyperplane, not a simple one? Seems to work on hyperplanes in this way.
I would assume it works because I'm pretty sure they're using some kind of deep neural net, and it works for them like so. Theoretically, there's nothing that's stopping it, because I just want an approximation of what's good, what's bad. I don't want to fit to your model exactly. In fact, in this, when I was training my SVM as an attacker, I intentionally tried to make the model bad, because I know the output that I'm getting is going to be bad and not complete.
So, as an intuitive solution for this, do you believe that combining multiple classifiers with any approach, like for simplicity, majority voting, something like this, will solve this problem, because your assumption, blind assumption about what's good and what's bad, will not work for all models? It will work for one, but it will not work for the others? I wouldn't say it wouldn't work for the others. Most of the time it does work for the others. But it could work better if I use different models. Is that what you're asking? Yes, if you use different models and took the decision from the fusion of those models.
It could work. That's something that we are trying to do, but we are trying to do it from a dynamic perspective. Like, if you have 10 different classifiers, is it better to combine all the results, or is it better to randomize so that somehow the defender gets confused about the adversary? So yeah, definitely that's one approach that could work, but if that's the best way to combine them, is majority voting the best way to combine them, that's something that we're still discussing.
Do we have some more questions? I have, maybe it's not related question, but when TJ prepared this presentation today, many of you are PhD students. Interesting question was, he had several papers which are in a process of publication. And today's presentation is, we are recording. Tomorrow will be on the web. Is it allowed to record results, tables, and all the data of your experimental results? You submit it and still are not officially published in the journals or at the conferences. Is that, in some sense, you are presenting results in advance of, because don't forget, the conferences and the journals, they are requiring original results. Is the result published on internet already making some copy results in the journals? Is that the result, again, original or not? I don't have the answer. I'm just telling you that was this morning the question.
I can tell you the answer. So typically archive is fine. It's not considered private publication unless it's nature or science. They want it to be completely virgin.
Usually journals you are signing that is original. They are
it has not been published in another conference or journal. Archive is not considered a publication.
Also, I have a comment that many publications I saw on ResearchGate Archive are published on the internet before even being accepted, and the full publication is published, not even results. And
that is if they accept, if they are requiring, if they are big, but don't forget, you are signing one document, you are very often not reading the details. You know, and they said, okay, sign that and send me before publishing. That is the reason. If that is the case, then it is. Then the question is different. You are publicly making available your results maybe 3 months or 6 months before they will be officially published. Is it worth? Is it, even if it is legal, is it acceptable? And because somebody else could use these results.
It could be an adversarial publication.
That's true. No, I'm just telling you what was my question. Yeah, it is dependent for presentations related, but it is not about the topic. Well, please, let's go back about adversarial attacks and the machine learning. Do we have some more questions? Yeah, please.
Have you tried any system to beat the attacks? Have you tried any kind of experiments on how to beat these attacks?
To beat the attacks? That is a tough problem. If I have an answer to that, I'll get my PhD this semester, but I don't have that. So there are different schools of thoughts on how to do that. One strong group of people believe that you have to make your model more secure, which was the example I gave you with the one-class classifier. And right now, the entire research is like gravitating towards making a more tightly bound classifier. But like you saw, I don't have a good theoretical explanation for that, but I have an intuitive way of saying why that's bad, because it kind of leads the attacker to where you are. So my first step is to show that that's not a good answer, because you are telling them exactly where to attack. And the second part of that is we believe that since the attacker is trying to play the game, we have to play the game with the attacker. We need to confuse him into going to a place where he can easily be detected, catch him, and then change our models over time. So it cannot be a one-stop solution. It has to be a cyclic approach where we have some information that always keeps us one step forward. So that's where we are trying to focus our efforts on.
Another legal question. How, after publishing this work, you make sure that no one will abuse it and use the approaches you are talking about to hack systems and to attack websites using captcha systems?
That's why the first line in my abstract and the last line in my conclusion is, we are not the bad guys, we are trying to help you. So that no one comes and catches me for that. Yeah. But yeah, it's going to get published. It's going to get published. If I don't do it, someone else will do it. So the best thing that Google or Amazon can do is make the systems more secure. Like, what else can you do? Like, they are going out and telling people they need to pay millions of dollars to use the system. They should know what can happen.
No, it is very important not to get impression that we are trying to modeling the ideal attacker, you know, and to analyze. But if you want to analyze and to protect from attacks, you have to understand that. And that was, this presentation is more about understanding the attacks, and it looks like is more advertising attacks by itself.
That's why I'm asking how to prevent abusing this approach.
Obviously, these attacks are very trivial. Let's be honest. That means it is not some sophisticated approach. You know, they are showing that relatively, with the standard machine learning techniques, relatively easy, you can make some kind of reverse engineering. So it is not that you are opening some very dangerous Pandora box. No, I think most of machine learning people will understand that there is nothing new novelty in this. The problem is, it is very difficult to find source, let's be honest. Especially for the people who understand deeply what is the machine learning and how to protect from these situations. And the other thing is very important, how to evaluate machine learning mechanisms and algorithms. That means, is the accuracy always enough to, you know, that is an additional warning for this presentation. Do we have some more questions?
And like a general question.
Sure.
Yeah. What was like the most challenging part in this experience?
Challenging part was when I started out doing this, there was not a lot of precedent, like references that were doing black box attacks on systems. Dr. Yampolsky sent me a paper on this 2 days after my proposal, and I was like, damn it, I just missed it by that much. But metrics were not defined. There are some metrics I haven't mentioned beyond accuracy, like things like diversity that I was mentioning from an attacker's perspective. There were no predefined, how do you measure diversity of attacks? Coming from that to making a field that is going to be like an interdisciplinary area was kind of like a challenge. And I have to sell it to cybersecurity and I have to sell it to machine learning. So, yeah.
So how does your work compare to adversarial neural networks?
Adversarial neural networks, from what I understand, especially the generative adversarial neural nets, they try to train the model better so that it is not affected by attacks in the future. It's kind of like trying to expect what attacks will occur so that you train the model to be more inclusive, like slightly. It's like taking that one class classifier and expanding a little bit more, I would say, from what I understand. But also they approach this problem as a static one. They say that if I can train my model to be good enough to understand what kind of attacks can occur, I will be able to ward off most attacks. But they also rely on the assumption that if an attack is too hard to do, an adversary will give up. So I don't know if that answers your question.
I would read a little more on the latest work in that, because it's really dynamic where you train two networks at the same time and they end up in equilibrium. You can't tell anymore whether it's real or fake.
Okay.
And that's the state of the art. That's how they produce realistic images, videos, because the network learns what the real model is and just duplicates it as much as possible.
Okay.
So,
and I think I also deal with targeted attacks when you have a set of samples that you want to take to the attack first. This is like more like an indiscriminate attack. We don't limit what samples can enter the system. So we are not bound by taking one spam email and trying to modify it optimally to go into the system. So we are talking more about like a general case study. So in adversarial machine learning, there's one group like the Ian Goodfellow's group that's trying to do the generative adversarial nets. There's another group from the paper that you gave me that started off, and they're trying to do black box attacks just per se. And I think this belongs to maybe the second category, which has probably less math, but talks more about the real problem that can occur from accessing a system via its API. But I should read that paper, you're right.
Okay, do we have some more comments, questions? If not, I would like to thank presenter TJ. And I assume that you will not need a perfect solution to finish your PhD.
If you say so, yeah.
Thank you. One more time.
Thank you.